Well, hello everyone, and welcome back. So in this last tab, we do another two-sample t-tests assuming unequal variance. And by the way, just to review what unequal variance means, I'm going to go back to the prior one. Unequal variance means that these two curves basically have different heights, right? And the reason they have different heights is because they have different standard deviations. So variance is standard deviation squared, so effectively kind of the same thing. And so this one's at 15, this one's at 19.91 as far as the standard deviation. The one with the lower standard deviation is taller. The one with the higher standard deviation is wider, because standard deviation indicates spread of the curve. So bigger number means more spread out, smaller number means taller and less spread out. Okay, so let's get back to this problem. So a software development company wants to determine if a new user interface design reduces the average time it takes users to complete a specific task compared to the old UI design. To investigate, the company randomly selected users and presented them with new and old UIs. Their completion times were recorded. At the 0.05 significance level, the company concluded that the new UI design reduces, yay, we finally get a one tail left, reduces the average task completion time. Assume that the population variances are unknown and unequal. So it's one tail left. Distribution is t, because we don't have population information about standard deviations, no significance. And this time, the alternative is that the new UI would take less time to complete the task for the new UI. So the reduces, that's why less than. Okay, so the new UI x bar equals average of these guys. The new UI standard deviation dot s of these guys, and the count of these guys. And for the old one, average standard deviation dot s and count. All right, and now we can see our two curves here. And as you can see, wow, there's almost no overlap. So this is almost certainly a reject. But let's keep going. So the hypothesized difference between means should be a 0, and what our expected variability should be is square root that squared divided by n plus that squared divided by that n, 0.76, and our observed difference is that minus that. Okay, so our expected variability is about 1. Remember that number could go either direction, right? And our observed is -8, so it's like at least 8 times, obviously more than, like around 10 times what was expected. So that's why this is for sure going to be a reject. But let's keep going. So it's the observed difference divided by the standard error. Okay, so it's actually worse than that, like 11 times. So we're way out here, right? Which means if you think about it, it's just a huge difference here, as opposed to, like, let's say one of these black dots had been here and one of the red dots had been, way over here just underneath it. Then that would correspond to the dots here in the middle with almost no difference between them. But here we have a huge difference between them. All right, so what's the probability of that? It's probably close to 0. So that's going to be t dot dist, and it's just the regular t dot dist because it's left looking, which is what the default really is. Degrees of freedom is that calculation that we're not making you do. That's true. Yeah, so 0%. I mean, obviously there's some numbers in here if I expanded this decimal, but for all intents and purposes, 0 chance. All right, so if looking back at this picture, what we're saying is, hey, there's no way that they can both fit within the same band, right? No overlap here. So they must come from different populations. So alpha 5%. Oh, well, by the time you get this exercise, this part will disappear, or I'll put some questions in there, one or the other. Okay, and then equals t dot inverse probability and degrees of freedom. Oops, shoot, forgot my comma. Probability, comma, degrees of freedom. Oh, and I didn't lock degrees of freedom, which is why that didn't copy. So let's lock it. And copy across, and then fix this one so it's looking the other way. 1 minus. Now, the number we're going to use, we're one tail left, so this is going to be our number, the negative 1.73. You can actually see it right there, the negative 1.73, but we are more extreme than that by a long shot, at negative 11. So that's why this is a reject the null. Our observed difference here was that number, and then we subtract from that minus the standard error, where are you? Our biggest number on the page, times the one tail left, because that's what we are. Oh, sorry. My bad. That's not right. We subtract. Remember, we always use even if it's a one-tail test, the confidence interval is always two-tailed, and it's always this two-tailed. So that was a fail. Okay, and then on this end, it's equal to that plus the standard error times the two-tail. All right, so here's our confidence interval. It obviously does not include the hypothesized difference of 0. And so what we're saying, to put this in English, what we're saying is, look, there is a difference between the two. We think that the difference is negative 8.47. In other words, we're shaving 8.47 seconds off. But at a minimum, we're shaving off 6.86 seconds, and we might be shaving as much as 10.07 seconds. So we're saving time. Now, depending on how many times this interface is used, like let's say this is like a call center and it's used, thousands of times a day, that could add up to some serious money. And then I'll let you work on the conclusions over here, and as I mentioned before, either you'll have problems here or I'll just erase this on your copy. And that's it for Prep 3-4. Thank you for joining us.